quite often get called out to diagnose why a pump might be noisy. And so the first thing I'd like to ask Keith, generally speaking, what are the things that could cause a pump to be noisy?
Well, the general reasons for pumps being noisy are, first of all, entrained air in the fluid, because then you're not dealing with an incompressible fluid, you're dealing with a fluid that's got air entrainment. And that entrained air can give rise to less than optimum operation of the pump, and that can be manifested in noise. Okay, so that's the first point. The second point the pump may be noisy is because you're not operating in the preferred operating region. And if you look at most pumps, most centrifugal pumps, we say you shouldn't operate more than 25% to the left of best efficiency and not more than 10% to the right of best efficiency. And that's covered in this new regulation for calculating MEIs for pump. So that preferred operating range for a particular size of pump is actually quite narrow. And many people are selecting pumps outside that preferred operating region. And in doing that, they have impacts on the hydraulic performance of the pump. If we talk about going to the left of best efficiency, once we get past about 25% to the left of BEP, we're going to run it into, first of all, discharge recirculation. And that's recirculation of the liquid at the discharge part of the impeller. And then as you go further to the left, you're going to start to run into suction recirculation, which occurs in the suction part of the impeller. And then finally, you're going to get to a situation where you're going to get either an NPSH mismatch and possible cavitation, but you're almost certainly going to get overheating and temperature rise in the liquid that you're pumping because you're too close to shut-off head. And all of those situations, you get increasing problems with noise. So most people, when they hear noise, the pump is cavitating. That's most cases not true. It's one of those other phenomena that I've just mentioned that is actually creating the noise. Entrained air, discharge recirculation, suction recirculation. Then you get the potential cavitation as you get closer and closer to closed valve.
So Keith, what does this do to the performance of the pump?
Well, the performance of the pump, hydraulically, it's quite clear. It affects the flow and head. As you close the valve or you get away from best efficiency point, you're going to have poor hydraulic performance. But long term, you're also going to get mechanical failure of components. You've got potential failure of mechanical seals, you've got potential failure of bearings, even potential failure of shafts. And it's not unusual to see mechanical damage to both impellers and casings when cavitation occurs. And that's from cavitation erosion, which is where the cavitation phenomenon causes mechanical erosion of the metal that the impeller is manufactured from.
Looking at this installation, this slideshow, is there anything that you can see that might not be quite right here? First of all, the elbow. Is the elbow too close to the inlet of the pump?
Well, under normal circumstances, in an ideal world, we should be looking for at least 5 pipe diameters between the bend and the pump suction of straight pipe, not connectors and flanges and so on. So we've got a situation here. Look at the pipe diameter here. We've then got our strainer, and then we immediately drop down to a much smaller copper pipe. That's not particularly good design, in my view, to take this smaller pipe into the suction of the pump. From a space point of view, I can understand why they did it, but it's not ideal from a hydraulic design point of view. What we should be trying to do is to put an eccentric reducer just here where we couple to the pump flange, and then we go with a much larger pipe back up to the suction strainer. So I don't actually like that, the way that they've done that. And obviously they built that on site. That's not something that's been a collection of components that have been bolted together.
And so, Keith, do you think that this installation might have benefited from the use of a suction diffuser rather than the strainer up there in the vertical and then the elbow into the pump?
Almost certainly. And if you're going to put a suction, if you're going to replace that strainer with a suction diffuser, you can actually get rid of that strainer because you can buy suction diffusers that got strainers built into them. So you can actually substitute this component with a suction diffuser. The other good thing about the suction diffuser is it might allow you to put your flexible connection just here rather than just here. There are things that you can play around with.
So looking at that slideshow, that picture, we see that up in the top right, there's a looks like stainless steel pipe that goes through the strainer and steps down to a smaller pipe and then goes through the flexible connection and then transitions to the pump inlet. This possibly causes turbulence and again could affect the pump performance.
Well, the critical thing for me is the velocity through this area. And I would like to see velocities of around 1 metre per second in the suction pipe work down here. Every time you decrease the pipe diameter, you increase the velocity of the fluid through that pipe. And that, from my perspective, is not good because remember that if you've got a high velocity going through here, when it gets to the eye of the impeller, we've got the veins of the pump chewing into that column of liquid. The higher that velocity is into the eye of the impeller, the more shock loading you're putting onto the fluid at the point where those tips of the veins actually intersect with the water flow. And that shock loading needs to be taken into account with the suction losses for NPSH, because that shock loading reduces the pressure at the eye of the impeller. And remember that the purpose of having NPSH is to make sure the pressure at the point that the liquid actually enters the impeller is above the vapour pressure at the pumping temperature. And anything that you do to lower that pressure is bad news.
What about if the inlet pipe was the same diameter as the suction flange? Would that be roughly 1 metre a second? Could it be?
Well, you've got to size. That's going to depend to a large extent on how fast the pump is running. Because if you look at a 4-pole pump, generally speaking, the flow velocities are lower than the same pump operating at the same duty that's running at 2009. If you check the pipe work, the flange diameters of the faster pump, they will be smaller than the same pump operating at 1450 RPM.